Good afternoon, and welcome to the Marposs Introductory Webinar Series. Today, I will be presenting the Braincamp Stamping Solution. This is an introductory level presentation for basic information regarding the Braincamp monitoring system and how it operates. My name is Joe Bortolameolli, and I am a product specialist for the Braincamp stamping line. I have been involved with metal cutting, cold forming, hot forming, thread rolling, and metal cutting for the past 30 years. We also have Rachel Ballard, our marketing specialist, as a panelist. We will have time at the end of the presentation for a short question and answer period. So you can type your questions in the appropriate area, and we will follow up at the end of the presentation. I would first like to give a brief introduction to Marposs. Marposs started in 1954 in Italy. We are a leading provider for gauging, inspection systems, and monitoring devices for the automotive, aerospace, medical, packaging, consumer appliances, and electronics industry. We are in 34 countries around the world and employ more than 3,700 people. Marposs has acquired 26 companies over the past 20 years to become a one-stop inspection, testing, monitoring company for the manufacturing industry. As we say, one partner, many solutions. Marposs is headquartered near Bologna, Italy. Brankamp was founded in 1977 and began its business out of Erkrath, Germany. It was acquired by Marposs in 2013. Marposs North America is headquartered in Auburn Hills, Michigan. Marposs also has branches in Canada and Mexico, where it provides sales and service for the Braincamp lines as well. Braincamp press monitoring provides slug elimination, broken punch detection, along with misfeed and other irregular force related issues. It also supplies machine protection along with aiding the operator in the setup and providing data to key personnel involved in the manufacturing process. All systems can be networked into an existing IoT structure. This video by Mr. Kruger will demonstrate our sensor technology. The sound is not good, so I will narrate over the video. This is a Variosound sensor, which is measuring the deformation of the structure inside an 8mm hole. In this case, it's mounted in a rock. As you can see, it is solid. If you squeeze the sides, you can see the force output on the oscilloscope. Here we are getting a reading from a solid rock, which shows how sensitive our sensors are. There are many conditions that influence the stamping process. Raw material can have temperature, thickness, and hardness variances. The material feed, the lubrication, the tool temperature and forming, and the machine setup. And of course, there's always the human factor. This will all affect the final product in quality and consistency. The force curve is always the fingerprint of the process, but all the curves have a reason. For example, here we can see the curve that we have in the process of this tool. The force is coming down, and now the stripper plate is hitting the material. As it comes through, we have punches that come through, and we can see the signal from that along with the coining. And here we have a drop in the force where the stripper plate is lifted right back up off the material. The basic principle of the process monitoring is that it receives various sensor signals from the machine. It takes the output signature during the forming process and produces a timeline of a signal strength. The monitor then puts an envelope around the signal to limit the variance. Once the curve breaks outside the adjustable envelope, the unit stops the machine, or it can sort out parts depending on the process. Here's a video explaining the different sensor applications. Here are sensors that are located inside the tooling and their different positions. We'll first demonstrate feed monitoring, which is the material jams up in the tooling. We monitor a single point for repeatability during the window of operation. You can see when the edge is detected outside of the program time window, it shuts the machine down. Next, we have the standard distance sensor. Instead of reading the peak force, like all other monitor devices, we monitor a signal with an envelope limit. This allows us to use the type of sensor with more sensitivity. We also have slug detection, which is one of the most popular sensor applications. We are able to pick up a large change in the force when a slug is introduced into the material. Punch breakage is also an application that we detect the acoustic change in the plate to discover the punch breaking off. Last is our standard force monitoring. We are designated areas of concern for the customer that the force is related to. If there are any inconsistencies in that force, we shut down the machine. And here are some of our monitors. Sensor position is important depending on what you would like to detect. The closer the sensor is to the area, the more sensitive the system will be, and the smaller the defect will be able to be picked up. As you can see in here, the sensor positions are far away from the process. The sensors in the tooling are closer and will be more sensitive. This shows an example of the signals changing according to how close the sensors are located to the critical area. These sensor signals come from the sensors located on the ram or the con rod. These sensor signals come from sensors located in the tooling. You can see the detailed difference with them. And here is the progression you have with the material going through the dies. Here you can see more details of what's going on. We have blanking, where it spikes in a certain area. We have drawing, which draws the material out a little bit. You can see how that affects the signal. The clanging is a hard operation. You can see that distinguished signal there. Piercing, it's a small pierce on this where it's thin metal piercing through, so it's not strong of a signal. And we have the trimming, which is a definite change in the signal down below at a certain time. With job memory, you can look at forces that occur the last time you ran the job. This will aid you in setting up the machine. The current curve will be black, and the reference curve for the last job will be blue. First impression shows the force is a little bit low. After adjustments, the signal comes up a little closer to the previous process. After finer adjustments, the signal gets the best results. This allows for more consistent setups. Another aid is to measure the stop block pressure. Looking at the punches hitting in the stop blocks, you can see the punches hitting and the stop block pressure. By slowly lowering the pressure, you can adjust the tooling and the machine reduces the overall tonnage used, which in turn saves energy along with giving your press a longer lifespan. Of course, this is not always the case. To reduce the stop block pressure, this depends on the tooling. Another solution is to optimize the speed of the machine. This will give you the most productivity for for your progress. As we can see here, it starts at 100 parts per minute. The signal looks stable. We then increase the speed to 200 parts per minute with no change in the force curve. Then we go to 300 parts per minute. We notice vibration in the tooling, and the signal is varying a little bit too much. So we slow the process back down to 250 parts per minute, where we still get more than double the production without any vibration issues, and we can run consistently. One of the best solutions we have is to detect slug marks. Slug marks are created by debris that comes back up through the tooling or forming and cause marks on the parts produced. As you can see, these pictures, the marks are very small. We use ultra emission sensors in the stripper plate to detect the bending while the slug is present. Normally, the distance of the sensor edges are not as sensitive, considering the distances are the same when there is a slug or without a slug. So the monitoring of position sensors don't work as accurate as our ultra emission sensor. Our newest solution is for high-speed stamping presses. The new Brooder presses are capable of adjusting the shut height on the fly. Adjusting the shut height resolves some issues that are temperature, speed, or material related. We monitor the tonnage on one or more of the stop blocks, and we can send out signals to adjust the shut height to change the tonnage on the machine. We start the process by integrating sensors into the stop blocks. The stop blocks are easily machined for sensors to be added, as you can see here. The process begins by getting a signal from the sensors in the stop blocks. They are filtered and limits put above and below the force. If the signal reaches one of the limits, the unit will react accordingly, sending a signal to the Brooder control. The Brooder control then has a set adjustment for every signal that it gets from us. Then it sends a signal to the press and the adjustment is made. This is normally done manually by the operator. With other machine makes, this involves stopping the press and manually moving the shut height up and down itself. From the Braincamp display, you can easily see how the system operates. There is an actual force bar. There are also limits above and below. If the limits go beyond this, the appropriate light will signal sending a pulse to the Brankamp, to the Brooder, to adjust the shut height. The system will also display the force over a long period of time. This is called the trend. You can see the coil is changed, the pressure changes abruptly. You can also see over a period of time when the signal gets lower and lower. This influences by the heat or wear of the tooling. This is a typical display for a Braincamp. We call it the cockpit view because it shows all components at once. You can go easily into any menu you would like with the touch of a screen. A typical setup shows you the counters, the max force, the trend readings, and the force curves all at the same time. This system also displays the job memory, access levels, machine speed display, and operating modes. Here we have a typical Brankamp system, the X3S. It is a smaller system with a 9-inch screen. And the screen is a cockpit design. It also has a colorful LED status bar above and below the unit. This is the X5 system. This is a 12-inch display that is capable of RFID cards to read operator information for different accesses and tracking information. As all our systems, it is capable of the see-through 4.0 software. This is our data collection software of the future. This is the X7 system. This is a 15-inch display that also uses RFID to read the operator information. This is more of a computer-based system and is capable of over 24 channels. This is more flexible than the rest and are capable of more options, of course. Here we can have benefits for the Braincamp system. Reduces cost because of the tool and machine damage. It also reduces complaints from the operator or from the customers. It also, you're able to set up, the operator is able to set up the jobs quicker. And if you're able to speed up the machines, you can be more productive. Plus, you're able to run extra time without an operator, or one operator can run many machines at the same time. By using the process data collection, you're able to take the information from the shop floor. By using someone in the office, they can go live at a glance at all the data available on the shop floor. Operators can be supported by more experienced people viewing the setups. Current settings can be evaluated and controlled. Going down on the shop floor is no longer necessary. With data collection viewer option, stored data can be recalled. Conclusions can be possible. If an event of production problems, behavior of machine and tool can be evaluated more easily. All relevant process data is available at a glance thanks to the tuning board display. Process monitoring settings are visible to all machines. If you discover problems during production, you can immediately initiate improvement measures and adjust unstable processes. As a result of the fourth industrial revolution, Industry 4.0 improved the communication and self-monitoring of manufacturing production. Marposs has kept up with this movement and makes our system compatible with current applications with its see-through 4.0 software. As you can see, our MES system can communicate with the enterprise resourcing planning and automated manufacturing. This system is sustainable on its own or works together with the customer's existing MES system. With See-Through 4.0, you can produce reports on production and machine performance, basic functions such as job comparisons, downtime, overall equipment efficiency, tool management, and maintenance management. The See-Through 4.0 software is flexible to modify existing forms and easily to modify so you can view as you would like. With the modern age of smart devices, Marposs has integrated its See-Through 4.0 into mobile devices as well. This makes manufacturing on the go more of a reality than sci-fi. This concludes our presentation of our webinar. You can contact me for further details at the email and number on this page, or contact Marposs Sales Group for your local sales engineer. Thank you for your time. We will now open the panel for questions. I can see, I have to check into here and see what I have. I don't know if something was available. I got here. I don't know if Rachel, if you can get in here or not.
Yeah, okay. So we've got a couple that I had. How does the acoustic sensor work?
Okay. Well, the acoustic sensor, it's misunderstood as a microphone, and it's not a microphone. It's a sensor that picks up on the vibration of the tooling. So we are looking at a certain frequency of vibration. So when you think of vibration, if you hit your hand on the table, it has vibration that you can feel on the other side of the table. We're looking at that type of vibration going through the machine. So any separate piece of metal will dampen the signal more and more. So what we do is we try to concentrate on a higher pitch frequency, because when a punch breaks off, it has a snapping sound or a higher frequency. So what we do is we monitor the curve at a certain time, because also when the punch breaks off, it's doing as it's pulling up from the tool. It usually snaps off. So we look at that certain time for a certain frequency, and we can detect the punch breaking from there.
Okay.
Right.
How many sensors are used for slug detection?
That's a good question. Slug detection, we have, depends on what your process is. Normally, slugs are picked up or are done in the first segment of the tooling. They have punches in the first and part of the second segment where the punches are pulling the slugs out, and the slugs are coming onto the material. Depending on how big the tooling is and how wide it is, we can get away with one sensor in the first segment and one sensor in the second segment, just in case the slug rides over into the second segment. Also, depending if it's a bigger section, we might need two sensors on each segment of stripper plate. So it could be from 2 to 4 sensors.
Okay. Does the operator have to turn the system on every time it starts up the machine to monitor the process?
No, it does not. It has a automatic information that when it starts up, it understands the speed of the machine is started up, and it automatically comes back in monitoring. We also have an interface that basically handshakes with the monitoring machine. And what happens is when it goes from the jog mode to the run mode, and then the machine starts up and the clutch signal is activated, it knows that the monitor needs to be turned on. So it will turn it on at that point. Also, when it goes from the run mode to the jog mode, the system will go into this mode called the setup mode. The setup mode doesn't monitor the envelopes, but it will monitor the peak forces, which will protect the machine in that case.
Okay, awesome. That's all the questions I had. If anyone has any more, go ahead and ask now, or if you happen to think of some later, you know, Joe's available to answer them via email and things like that.
Okay. All right.
All right.
Thank you very much.
All right, I think that's all we have.
I'll put the control over to you.
All right. Thanks. Have a good one, everyone.
Thanks.